Welcome to our internet classroom for A-level chemistry. Today's lecture is about mole calculation, the stoichiometry of equations, the significant figures, percentage composition of mass, empirical and molecular formulae. When reacting chemicals together, we may need to know what mass of each reactant to use, so that they react exactly, and there is no waste. To calculate this, we need to know the chemical equation. This shows us the ratio of moles of the reactants and products, the stoichiometry of the equation. The balanced equation shows this stoichiometry. Take this reactions as an example. 1 mole of iron oxide reacts with 3 moles of carbon monoxide to form 2 moles of iron and 3 moles of carbon dioxide. The stoichiometry of the equation is 1/3/2/3. The large numbers that are included in the equation are called stoichiometric numbers, such as 3, 2, and 3. In order to find the mass of products formed in a chemical reaction, we use the mass of the reactants, the molar mass of the reactants, and the balanced equation. Now we check it out in an example. Magnesium burns in oxygen to form magnesium oxide. The equation is given. We can calculate the mass of oxygen needed to react with 1 mole of magnesium. We can also calculate the mass of magnesium oxide formed. Here are 2 steps. The first is to write down the balanced equation. The second is to multiply each formula mass in grams by the relevant stoichiometric number in the equation. So we do the calculations. From this calculation we can deduce that 32.0 grams of oxygen are needed to react exactly with 48.6 grams of magnesium. And 80.6 grams of magnesium oxide are formed. If we burn 1215 grams of magnesium, which is 0.5 moles, we get 20.15 grams of magnesium oxide. This is because the stoichiometry of the reaction shows us that for every mole of magnesium burnt, we get the same number of moles of magnesium oxide. Here is another example. Iron oxide reacts with carbon monoxide to form iron and carbon dioxide. The equation and relative atomic mass are both given, and calculate the maximum mass of iron produced when 798 grams of iron oxide is reduced by excess carbon monoxide. The process is the same as the previous one. Firstly, we write down the balanced equation. Then we get the mass of 1 mole iron oxide and the mass of corresponding product, 2 moles iron. At last, we simply used ratios to calculate the amount of iron produced from 798 grams of iron oxide.
We can find the stoichiometry of a reaction if we know the amounts of each reactant that exactly react together and the amounts of each product formed. For example, if we react 4.0 grams of hydrogen with 32.0 grams of oxygen, we get 36.0 grams of water. This ratio 2/1/2 is the ratio of stoichiometric numbers in the equation. We can still deduce the stoichiometry of this reaction even if we do not know the mass of oxygen that reacted. The ratio of hydrogen to water is 1/1. But there is only 1 atom of oxygen in a molecule of water, half the amount in an oxygen molecule. So the mole ratio of oxygen to water in the equation must be 1/2. When we perform chemical calculations, it is important that we give the answer to the number of significant figures that fits with the data provided. The examples show the number 526.84 rounded up to varying numbers of significant figures. When you are writing an answer to a calculation, the answer should be to the same number of significant figures as the least number of significant figures in the data. Here are some notes about significant figures. Note 1. Zeros before a number are not significant figures. For example, 0.004 is only to one significant figure. Note 2. After the decimal point, zeros after a number are significant figures. 0.0040 has two significant figures and 0.00400 has three significant figures. Note 3. If you are performing a calculation with several steps, do not round up in between steps. Round up at the end. How many moles of calcium oxide are there in 2.9 grams of calcium oxide? If you divide 2.9 by 56.1, your calculator shows 0.051693. The least number of significant figures in the data, however, is 2 because the mass is 2.9 grams. So your answer should be expressed to two significant figures, as 0.052 moles. We can use the formula of a compound and relative atomic masses to calculate the percentage by mass of a particular element in a compound. Now, here is an example. Calculate the percentage by mass of iron in iron oxide. After the calculation, the percentage mass of iron equal to 69.9%. The empirical formula of a compound is the simplest whole number ratio of the elements present in one molecule or formula unit of the compound. The molecular formula of a compound shows the total number of atoms of each element present in a molecule. Here are some rules. The formula for an ionic compound is always its empirical formula. The empirical formula and molecular formula for simple inorganic molecules are often the same. Organic molecules often have different empirical and molecular formulae. Here are some examples. For water, sulfur dioxide, and butane, the empirical formula is the same as molecular formula. But, for hydrogen peroxide and cyclohexane, things are different. The empirical formula can be found by determining the mass of each element present in a sample of the compound. For some compounds this can be done by combustion. An organic compound must be very pure in order to calculate its empirical formula. Chemists often use gas chromatography to purify compounds before carrying out formula analysis. An empirical formula can also be deduced from data that give the percentage composition by mass of the elements in a compound. The molecular formula shows the actual number of each of the different atoms present in a molecule. The molecular formula is more useful than the empirical formula. We use the molecular formula to write balanced equations and to calculate molar masses. The molecular formula is always a multiple of the empirical formula. For example, the molecular formula of ethane is 2 times the empirical formula. In order to deduce the molecular formula, we need to know the relative formula mass of the compound and the empirical formula. As a summary, we have talked about mole calculation, the stoichiometry of equations, the significant figures, percentage composition of mass, empirical and molecular formulae. That is all for today. Have a nice day and bye.